So we have one section in chapter 2 to finish up, section 2:7. And this is an idea that you should have also hit in some earlier course. And the idea of inverse function, really, it's at the very heart of it is, if you have a function, there might exist another function that does the opposite of what that function does. So if you have a very, very simple example, the symbol for inverse function is f, like that. And that sometimes confuses people. This is not 1 over f. That does not mean reciprocal. Right? Like a negative 1 power normally means 1 over. This is a symbol that means inverse of f. There we go. So in this case, what would the opposite function be?
5 over x.
What does this function do to a number when you plug it in? You plug a number in, what's the function do to it? Divide by 5. So what would the opposite function do? Multiply that thing by 5. Yeah, so those would be inverse functions. One function undoes what the other one does.
So you just kind of do opposite signs for the inverse? Or like...
The more complicated your function gets, the harder it is to tease out what the reverse would be. Do you see what I'm saying?
Yeah.
In fact, there's going to be a whole discussion about when does an inverse exist. Yeah.
So what an easy way to say the function times its inverse equals 1, basically?
Well, let's see.
Yeah.
Not really times, but what would happen if I did this? Oh shit. So what am I plugging into f? What is f inverse? 5x, right? And what does f do to anything that you plug into it? Yeah, it takes whatever it is, divides by 5. And so those cancel and you get x. Let me let you guys absorb that for a second. On one hand, this is almost too easy of an idea, and then you get lost in all the symbols and so forth. But if these two really are opposites of each other, they should effectively cancel each other out. So you should get left with x. Whatever one function did to x, the other function undoes it. So of course you end up with x. You end up back to where you started. How are we doing so far? Does this sound familiar? Hopefully you've talked about inverses somewhere before. But if it's been a little while, I'm going to go into a little bit more. Let's look a little bit more closely as to what this would mean visually, graphically, using these same functions here. What is f of 10? 2. What's f inverse of 2? 10. And it should kind of make sense. Whatever one function did to something, the other one's going to undo it. So in general, if f of a is b, f inverse of b will be a. So it just reverses the x and the y. How we doing so far? So an inverse function should do that. Because it undoes what the other function does, it takes all of the outputs from the first dude and makes it the inputs for x. So it switches what the output and input are. Okay. So what would this mean graphically? How would I graph an inverse function given a function? Somebody help me out. See an eraser in here? Uh-oh. I'm gonna do. Oh, wow. I've never seen a cool one. All right. So, for example, if I had this graph.
Write this graph paper 1/4 down.
Say again?
Write this graph paper 1/4 down for you. On
Yeah.
the other side.
Polar. Okay. So if I had this. Yeah, I don't like this. So if I had. Here's where I got to be a little careful. So we'll talk in a minute about what I'm being careful about. So this is the point, -4, -3. 2, 0, 1, 1, 2, 4. So if I have a function that looks something like this, what would its inverse look like?
Just flip the x and y coordinates.
I love it. So exactly what we discussed over there. The fact that it should make sense that it's going to undo what the other thing did, so that one guy's outputs become the other guy's inputs. The x and y effectively switches. So graphically, what's my f inverse going to go through? This goes through -4, -3, so my f inverse is going to go through
-3.
-3, -4. 0, -2. Of course, 1, 1 flipped is 1, 1. 2, 4 flipped is 4, 2. And you know I'm going to give you a problem just like this. I'm going to give you a function. I'm going to say, graph its inverse. That's all you have to do is flip the points around. That's really kind of cool what happens visually with this. When you graph the point -3, -4, it's right there. 0, -2, 1, 1, and then 4, 2. So the black line would be f inverse. Can anybody tell me where would the mirror be? Yeah.
Y equals X.
I love you were like, I know what he's going to ask. Yeah, exactly. The mirror, where's the reflection really? It's right down this line. It's going to be right down the y equals x line. So it kind of makes sense. If y and x switch, they should flip over the y equals x line. Yeah.
So were they always going to have a common point?
Only if the original had a point that had x and y equal. Right. I could have very easily kept this one up here entirely, and the other one would have been down there entirely. Right.
But they always mirror.
They always mirror each other. Exactly. Cool. So, the thing I had to be careful about when I drew that purple line, to make it have an inverse. So now we're going to talk about what functions have inverses. Not every function has an inverse. And the whole idea of having an inverse means I should be able to say, okay, if my output is -4, what must my input have been? -3. So, I mean, this is turned around, but you get the idea. I should be able to say, if I have this output, where did it come from? So what kind of function would I not be able to do that with? What function? Let's start off with don't have inverse. The most simple example of one that would not have an inverse.
This is line.
Well, specific kind of line, but yeah. And this is because if an output is 4, if I told you the output for this is 4, what must the input have been?
2, -2.
See, you can't tell me. I just did something in my head. I picked a number and I squared it and I got 4. Can you tell me exactly what number I just squared? No, you can't. Because there's 2 options. You with me? You guys see what I'm saying? So I had to be careful and not allow this to do what that does.
Has to pass the horizontal line test?
I love it, right? It can't, if one side is here, the other side can't also be at that same point. That would mean that those 2 inputs have the same output. So that equates to, so what do you have to do to be a function? You have to pass the vertical line test. Every x can have only one y. But now we're saying every y can have only one x, so I know where it came from. So it's got to be both ways. So if it's vertical line test for x equals 1y, it's horizontal line test the other way. So this is not invertible. Doesn't pass the horizontal line test.
So absolute values as well.
Yeah, anything that comes back on itself in this direction, right? So to be a function at first, it's got to pass the vertical line test. But if it's a function that comes back on itself, so that's why when I was drawing the purple graph, I was trying to make sure I wasn't going to go down here. I had to keep going up or keep going down. So I'm not going to be across from myself. Yeah.
Does that apply to square roots?
Well, square root, and actually any root, what do they look like?
kind of like a half parabola.
Yeah, exactly. It's a half parabola. That's the trick. The inverse of x squared should somehow be the square root of x. And I don't know if that's why you're asking. This should have an inverse. And it does as long as I force it to. Now again, how many of you guys have already done trig? Do you remember talking about inverse trig functions? And then be careful about the domain so that it actually existed.
Yeah, like.
And you talked about all that stuff. So if I have a parabola, one way to make sure that its inverse exists, what's the only way I can kind of force this thing to pass the horizontal line test? If I'm allowed, I am God. I can come in with my eraser and change things. If I just destroy half the poor dude, right? So then this is y equals x squared with x greater equal to 0. Now does it pass the horizontal line test? Hell yeah, every horizontal line only goes through once. And if I do a really quick turnover, it looks just like an radical x function, right? So it would be. You guys with me? So in order for an inverse function to exist, I have to have a situation where I have only one output for every input and one input for every output, right? So if another way to look at this, if I flip that whole picture over, what would it look like? If I flip that whole picture over this line, it would look like that. Is that even a function?
No.
No. So I can flip it and then check it with a vertical line test. Or I could just say, screw that, let me flip my test. I'll just check the original dude with a horizontal line test. Save myself the trouble. Does that make sense? I like it. So there's several different ways to look at the same thing. Okay, so let's get a lot more specific. You know you're going to have a problem. We're going to give you a graph. You're going to have to graph the inverse. It's relatively simple. Just switch all those. I'm going to ask you first, is it invertible? And let me actually go ahead and put the actual name of this thing. If a function is invertible, and what name really makes sense? In order to be invertible, not only does every x have to only go to one y, but every y has to only come from one x. So it's one goes to this guy and the other one goes back, 1 to 1.
It's a one-to-one function.
It's a 1-to-1 function. So an invertible function is a 1-to-1 function. Have you ever seen that equal sign with 3 lines? That's like a definition. That is that, and that is that, by definition. So 1-to-1 function means it's an invertible function. It passes the horizontal line test. So we did the very first thing we did was we looked at a really simple function. X divided by 5. And then we said, what's the opposite of that? Multiplying by 5. So now I want to figure out, is there a process where no matter how ugly the function gets, is there a way just to find its inverse if one exists? So there is a process that does that. So for example, if I had that thing, and I want to find f inverse. First, can anybody argue very quickly why this should be invertible? Why is this 1-to-1?
Cube root.
Cube root looks like what? Somebody's going to say, it looks like that. No. Cube root looks like what?
Like a.
Yeah, like a square root that's got its other half, and it just keeps going up, and so it passes the horizontal line test as long as I don't make that look horizontal. It goes up and up forever, very, very slowly. So it completely passes the horizontal line test, right? And it has no trouble with the backside, so it doesn't need It doesn't need a domain that's restricted. It ought to say x greater than 0. Yeah.
So does it have to pass the vertical line test and the horizontal line test?
Yeah, if it doesn't pass the vertical, I'm not even talking about its inverse at all. Okay. It's not even a function to begin with. Yeah. So this is definitely an invertible function. How the hell do I find the inverse? Who already remembers how to find its inverse? You actually, the really cool thing is you do the exact same thing as you would visually. How do I find the inverse graph of a function? Switch the x and y. It's exactly what I do. Where's the y? Beautiful. So I took the place of y. So I always draw a little dotted line to tell myself I'm do something, I am applying an idea. I'm not doing something algebraic, right? I switch the x and y. I don't stop there, that's not good enough. I have to resolve for y. And look what happens in the process. How would I start to solve this for y?
Plug in first.
Subtract 7?
Yeah, subtract 7. So just solve for y. Get y by itself. So subtract 7. Keep going. How do I solve for y?
Cube it.
Cube it. Get the hell of that cube root out of the way. Cube it.
And then add 4. Or subtract 4.
All right, subtract 4. And then
Divide by negative.
divide by negative 2. So you get, put it up here. So you get f inverse equals this business here. Which you can also write as that. Is that cool? I can take that negative off the bottom and just change the signs on the top. Whichever way is fine. And it should be true. The inverse of a cube root should essentially be a cube. I just don't really necessarily know where everything else goes, right? But what does this process do that's kind of like, well, duh, this should work. It takes all the operations that are there and does the opposite of them. As I solve for y, I'm doing the opposite of everything that's there. And it's all collecting on this side. So I call this Memorex over here, right? It just remembers all the opposite things you're doing. So that should be the inverse function. It is all the opposite stuff in the opposite order. Yeah?
So when it has the parentheses, do we have to factor it out?
Oh, please, I'm glad you're saying that. Don't do that to yourself. No real need to do that.
Even if it's just squared?
Even if it's just squared. Yeah. And you'll see today, actually, when we get into chapter 3, that leaving it like that is actually a little closer to what's known as the standard form. Yeah. Okay. How do you guys feel about that? Okay, cool. So that's basically 2.7. Cool. Okay. So that is what I'm going to assume to be basically the end of old stuff. I mean, it's definitely the end of chapter 2. It doesn't matter my interpretation of that. But everybody should have seen inverse functions at some point. And if you haven't, or it's been a while, there it is. Right. So you can definitely expect from me a couple problems with find the inverse. One problem with, here's a graph the inverse. Okay. So what we're doing now, section 3.1 might have some new stuff in it. Section 3.2 definitely will have some new stuff in it. And the very first thing I want to do is do a little review of something called completing the square. And there's very often we run up against something like this. How many of you guys have heard of completing the square? Okay, cool. You might not remember exactly how to do it, but maybe you do. But the early uses of completing the square make it seem like we don't need to know it at all. Why would we do that? Because we actually prove quadratic formula using this. And then if I was a student learning, I would say, well, why the hell use that anymore? We've got something better. We've got a shortcut. Well, because this actually helps us put equations into what's known as standard form. So, for example, I don't know if you guys remember this or remember seeing this? That would be the equation of a circle. What would its center be?
X minus H, Y minus.
So what would its center be? 0, 0. Its radius would be 5. Its center would be at 0, 0. So if I do this, and I think about it in terms of transformations now, right? This would make my center go from 0, 0. Where would it go from there?
To the left.
Careful.
Right.
To the right. And down 4. I love it. When it's inside with the variable, it's the opposite of what it is. Right? When you see a minus, it actually goes right or up. So here this would go right 2 and down 4. So my center would now be there. And then it would have a radius of 5. So that's really horrible. But very quick. But the problem is, it's not always going to be given to you. It's going to be given to you like this here, maybe.
Nice.
So how do you collect all this shit? Make it look like this? This, right? And of course, there's further uses of this later in mathematics. But unfortunately, very often when we first hit a new idea, we're not far enough along to really see the full usefulness of it. And we sort of kind of write it off sometimes. But there's always somewhere later that you want to use this thing for. So first off, what the hell is this? Let's see if I can go through this semi-quickly. Here's a little motivation, like we're in drama class. Little motivation. What do you get when you FOIL that out?
X squared plus 8x plus 6.
Yeah, so x squared, 4x is 8x. 4 is 16. What do you get when you FOIL that out? It'll be x squared
Plus 49.
minus 14x plus 49. What keeps happening? That middle number is double that, and the last number is that squared, right? Always, no matter what the hell you do, it's going to come out that way. So completing the square is actually going backwards. It would say, if I have this, what would I have to put here to make it factor? Now you see why it's called completing the square. What do you have to put here to complete this so it can be rewritten as a square? Yeah, what are the 2 steps? You basically undo what we saw happening up here.
Take half of 10.
Good. Take half of 10 and then square. Yeah. This is what has to go here. And the really kick-ass cool thing is that is how it factors. X plus 5. So I see several very confident people out there. So let me give you a harder problem. You try this one. So, I mean, this little thing right here being the answer there makes all of these relatively simple. You almost don't have to think about it. So, what's the first step? Take half of -9.
Negative 4.5.
Don't go there. Yeah, square it.
20. Negative. No, it's positive.
9 squared,
81 halves.
2 squared.
4.
Okay, cool, right? I don't see decimals in there, don't give me that crap. Because very often you're going to have other fractions in there you want to put it together with. If you throw decimals in too early, it actually makes it more difficult to look at. You should be able to handle the fractions. So what do I put there? Yeah, plus 81 over 4. And then how does it factor?
X minus 9.
Good, x minus 9 halves squared. I love it. Cool. Yeah.
Are you always going to divide by 2?
Yeah, the 2 steps here are always the same. Cut the middle dude in half. And then, I could say b. You have ax squared plus bx plus c. So cut b in half and then square it. That's always going to be what goes in the answer. That's always going to be what has to go here to make it work.
Okay.
Always. Now notice one thing. So far I've always made a 1, right? And this is built off of a being 1. So what the hell if a is not 1? Yeah, let me make something really nice and gross. Cool. I like it. So what you actually have to do, it's built off of that first thing being 1. So you have to take 3 out.
11
Yep. There'll be a 3 out here. Okay. So that much we know. There's a 3 out there. Now try it out. Try to finish that out. Really good example why I don't use decimals. You can never fully represent this fraction with any decimal unless you put bars in there and then it gets free.
121 over 33.
Yeah, first step is cut this thing in half. So if it's a fraction, just actually cut it in half directly, right? Don't divide by 2, that gets a little freaky. I always get somebody tell me it's 22 over 3, the 2 goes in the wrong place. It's got to be on the bottom, it's dividing, so it's 11/6. Second step, square that. 121 over 36, I love it. So what do I put here? Yeah, 121 over 36. So how do I factor it? 11 over 6, I love it. I don't care how ugly I make the number in the middle. It's always straightforward. You barely need any thought. Besides just doing this right and then squaring correctly, that's the only real thought involved. Now real quick, just to lead us into the next thing, what did I actually add to this side? I did not add 121 over 36. What did I actually add to this side of the equation? I added 3 times this, right? Whatever number I put there, it's automatically multiplied by 3. So what did I actually add to this side? Even better? 121 over 12. Cool. I like it. It's all right. That becomes very important when you do what we're actually going to do with this. This is just a review of completing the square. So the reason we did that is because in section 3.1, the very first thing we talk about is quadratic equations. Standard form. And most things standard form is, you can equate it to the idea behind y equals mx plus b. Like with the circle we did earlier. If I put something into standard form, I can see what its center is, I can see what its radius is, so forth. Well, that's neat, Joe. You guys with me? Just like if I solve a line for y, I can see what its slope is, I can see what its y-intercept is. It's really kind of cool. If I put a quadratic equation into standard form, it's going to end up looking like this. And anytime I see something that looks like this, it tells me completing the squares in my future. Because then I'm always going to have it together. They're going to have it in parts, and then I got to put it together using completing the square. So the vertex would be what? For this, the vertex is 0, 0. Right? For an x squared, the vertex is 0, 0. Where's the vertex for this? How has it been shifted?
Negative h.
Careful. Yeah, h. Up k. So hk. Well, they use the same letters for the center of a circle. They use HK for almost everything. I have no idea if there was a Howard Kuchenstock or something in the past, maybe. I don't know why he chose H and K, to tell you honestly. Howard Kuchenstock, I like that. So here's an example. Let's do one that's already been put together, just to kind of see if we're able to handle everything you're going to have to do with it. Let's do one without an A yet. Let's see. So somebody help me out. What's the vertex?
Negative 3, negative 1.
That's right. Negative 3, negative 1. What's the y-intercept? And everybody always screws this up. No, a lot of people very often screw this up. It's not negative 1. Don't feel bad if you think that, because it's been ingrained in your brain to look at the number by itself, but it's only if it was in this form here, then that's going to be the y-intercept, because when you make x 0, that's what's left. But when you make x 0, what do you get? 9 minus 1, 8. So the y-intercept would be 0, 8.
So you just set x to 0 to find the y-intercept?
Exactly. Here's the beautiful thing. It sounds like a note coming up, because I've slowed down. To find the y-intercept, you make x 0. To find the x-intercept,
y0.
you make y 0, of course, right? For some reason, we forget that. It's always that easy. In fact, in my last math course, Math 896, I think it was, we had equations with like 28 letters. We had to borrow from other alphabets. But if I wanted to find the w-intercept in this 28-dimensional space, if I want to find the w-intercept, what did I do? I made every other thing 0. It's silly. That idea carries. We only have 2 freaking variables right now. So if I want to find one guy's intercept, I make the other dude 0. That's going to force him to tell me, okay, when x is 0, where are you? I'm there. Okay, shit. When y is 0, I'm there. So that's what happens when we force a variable to be something. We're forcing it to tell us something.
So what would be the x-intercept for that?
I love it. What would be the x-intercept? How would you set it up?
0 equals x plus
Yeah, 0 equals... How would you solve that?
Solve for x.
Add 1. I would so not FOIL this out, right? Missing one word. Square root both sides. And when you square root, what do you have to do?
Plus or minus.
Plus or minus. Does this sound familiar? When your variables are already collected as a square, you can solve it very directly this way. You don't have to multiply that out and factor. You don't have to do all that crap. So I get x plus 3 equals plus or minus 1. And then I have students that ask me where the plus or minus key on the calculator is. It's not a good sign. It's sort of like, where's the any key? It says hit any key. So what would I do here? What are my two x-intercepts? -3 plus 1, -3 minus 1, right? I just do the plus and the minus separately, so I get -2, -4. I love it.
Why do you put the plus or minus there in the first place?
Because
Sometimes you do and sometimes you don't.
what we're really doing, look at a very simple example like this. 2 reasons. I'm going to give you 2 reasons. One reason is I could pull that 9 over, factor, and then I see 2 answers. Don't I?
Yeah.
So any other way I do it, I better get those 2 answers. Now, in a way, that's kind of lame. That's not really, I'm like, okay, you just got to make sure you got 2 answers. It doesn't really explain why. The second way is, I don't know if you guys remember, what is the square root of x squared? It's not x. It's the absolute value of x. So instead of doing that to ourselves, we just skip this step and say x equals plus or minus 3. That's what that would mean, isn't it?
Yeah.
And the absolute value equation is going to have 2 answers to it. 2 cases. I love it. So that's why we just choose to do this. Just go straight to that.
Do you do that for all radicals? Do you always do the plus or minus 3, or is it only the even?
It's the evens. Yeah, we are a little far away from realizing this, but this problem, it only has one real answer. 2. -2 would not work here, right? See, it's the whole idea of squares always turn on themselves. That's why there's always 2 possible inputs that give me a certain output. The cube doesn't. There's only one real input that gives me this. And now some of you guys are saying, why is he saying it like that? How many answers should there be to this equation? 3 answers. 2 of them are not real, and we haven't officially reached that section, although you should all have talked about I at some point in the past, complex numbers. So we're not quite there yet. So right now we say officially this has one real answer. Later we'll be able to get all 3. You have the 2 complex answers.
So if it was like x cubed equals -8, would that just be
Negative 2.
imagining?
Yeah.
Oh.
Cube root of -2 is, cube root of -8 is -2. Cube roots, odd roots are laid back. They can handle negatives.
So it's
Even roots, they freak the hell out.
So only evens have plus or minus or imaginaries?
Only even roots have plus or minus.
Oh, right.
This doesn't have an imaginary part to it, but the equation has imaginary answers that doing this doesn't capture. You guys come out? And again, if you pull the 8 over, oh shit. How do you factor this?
X minus 2.
Good?
And then X.
Yeah, one of each, right? 1x, 1, 2.
Then x
So I need the other 2 x's,
X squared.
the other 2 2's, and the middle guy is
plus 2x.
good, plus 2x. Can't you solve this using quadratic formula?
Sure.
That would be your 2 complex answers. Okay, cool. So, one last thing here on this problem. How would I graph this thing? Okay, cool. So obviously I kind of gave away. I mean, the y-intercept is 0. Just start putting in your known stuff. The vertex is right there. So -3, -1. -3, -1. So let me ask you this question. Where is this parabola's mirror at? Every parabola's got a mirror somewhere that goes right down the middle of it, right? So obviously every parabola's mirror is going to go right through its vertex. So the mirror would be right here. This is called the axis of symmetry. Which means, now stay with me. I know we know 2 other points, but sometimes these x-intercepts are disgusting, or they're not even real. You with me? But I know we got two x-intercepts there. We're going to make sure that we actually go through them. But can anybody tell me, just from what I've drawn so far, can anybody tell me one more point this thing goes through? If that's the mirror.
-4.
How do you mean? I'm sorry. Yeah, 3 over. So 3 over. So it's got to have a mirror image of that. So it's got to be 3 over on this side and up 8, right? You with me? So that's that one point you can always get. You can always get the y-intercept. Always. It should be easy to get. Just make x 0. Then you can always get its reflection, and you got the vertex. That's all you need. Now I'll still ask you to find the x-intercept. Just make sure you can. So if I graph this, I'm not even going to try to graph it carefully. Let's see how close I get to what I'm supposed to. It's supposed to be -2. All right, make it big. -4. Yay, Jeff. Yeah, just make it big. You guys kind of with me? The fewer points you use, the less precise. But for parabola, all you need is the vertex and a couple other ones just to show you how fat the dude is. Right? If they're really there, it's a skinny little dude. Out there, it's fat as hell. Okay. All right, maybe. So you're going to have exactly that kind of problem. I'm going to give you, and I'm not going to give it to you like this. I'm going to give it to you not put together yet. You put it together, you get the vertex, you get the intercepts, and you graph them. Yeah.
How do you know which x's to use for each plot point? Like how there was a -2 and then a -4. Like how it's -4, 8, but then there's -2, 0.
Well, x-intercepts really should be written as points. Right? If I make y 0, when y is 0, x is -2 or -4. So those are the points. Is that what you're talking about? Okay, cool. Whenever you find intercepts, you're making one of the variables 0. And you're finding the other part of that point. Cool. Okay. So let me give you this, and let me let you look at it and see what you think. I've I got a couple problems worked out, but they're not graphed yet. And at the very top, I left out the A dude because I was thinking about the first example I was going to do. So the general should have an A there in case you have a constant that you have to take out. So I'm hoping, if it's been a while since you did completing the square, this should hopefully help you remember the steps. But it's also got that one little weird piece that some of you guys might remember. When you're working entirely on one side of something. And take this here away. Is that cool? Let's have one person go, wait, right about now. Okay. So if I have just a function sitting there. And I want to put this into standard form. So of course, what do I have to kind of do first? And there's a little extra stuff we're not used to having in the way. What do I have to do first?
Take out the 2.
Take out the 2, but take it out of what?
Everything.
No. Thankfully not. Because I know my end result is going to be this. Yeah, there. So I know I'm going to have some stuff outside that collects together to become K. So all I'm really concerned with first is getting all my X stuff together. That's completing the square. Completing the square only cares about this part. It says your X stuff is not together yet. So when I take a 2 out, I only take it out of that much. And the plus 1 is just sitting out there waiting. And now you attack that stuff on the inside, you attack it with the 2 steps. So this is where math intersects with Indiana Jones, believe it or not. You guys have all seen Indiana Jones? I know it's almost 20 years ago when it first came out, but come on. So he took a little gold statue and he put this back in his hand and he didn't really balance his equation out very well. That's where the boulder came in almost straight, right? So whenever I do something to, if I take something away, I better add it. So overall, I didn't do anything. And now look for the boulder. So what are the steps here? They're very easy for this dude, right? Cut them in half, square them,
4.
Put the 4 where?
On both sides, inside the parentheses.
Just so I put the plus 4 here. Alright, so 2 levels of this. What did I actually just do?
Plus 8.
I just added 8. Right? Isn't my original function this? So if I multiply this back out right now, wouldn't I get, then I just add 8? So that's why I have to take that into account. First, I just added 8. So I better at the same time take away 8, so overall I didn't do shit. Right? So I better put a minus 8 out there at the same time. I'll let you absorb that for a second. I like the look of it here. So is everybody cool with, if you take that 2 through, you can see it's 8 that you just put there. You didn't put 4, you just actually put 8. So if you keep going, if I don't put that there, I don't get the original function back, do I? I get plus 9, so I've got to subtract 8. So I get back to 1. So whatever you put inside, take the coefficient into account, and then you better undo it. So overall, you didn't just do anything. It's really the same exact idea, you know, when you have, what you got, Jeff? 3/6, you want to reduce it. What do?
1/3.
Divide by 3. Now, if you only divide by 3 on the top, you're going to get the wrong answer. You better divide by 3 on the bottom. So overall, what did you actually just do? You just divided by 1. So you didn't do shit. You just made it look different. We're doing exactly the same thing. We're not actually changing it. We're just making it look different. So what do I end up with here? How's this thing factor?
X minus 2.
Yeah, x minus 2 squared? Minus 7. Cool. So what's my vertex?
Choose the negative 2, -7.
Careful.
Oh, negative
Yeah.
2, -7.
Positive 2. Negative 7. Cool. That's your vertex. What's your y-intercept? I've actually got it circled. 1. Yeah, so don't look at this. Look at that. From the very beginning. See in the handout, from the very beginning, you can tell what the y-intercept is. This is a much better form to see the y-intercept. Right? So get what you need from where it makes more sense. These are both the same function. Who cares where you get it from? I can see 1. There you go. 0, 1 is the y-intercept. If I wanted the x-intercepts, I could solve this equal to 0 and solve it. I'm not going to ask for it right now. And then you can graph this problem, right? It would be the y-intercept is at 0, 1. Vertex is at 2, negative 7. Where's one more point? Two over, so 4, 1. So that would be the one that we got by reflection, right? The reflection of the 1 point that we already did. You can get the y-intercept, mere reflection point without doing any work that kicks ass. And that's all you need is 3 points. The vertex to see how far up or down it goes, and the 2 points here to see how skinny or fat it is. Yes, sir?
For the vertex, why is x positive 2?
Remember, so this goes back to transformations. Every input, since the first thing I do is subtract 2 from them, every input has to be 2 bigger than it was before. That's why it moves right. Yeah, so don't forget, when it's inside with the variable, it's the opposite. When it's not with the variable, it's exactly what it says. Yes, sir?
I quite don't understand right there. Second part where the two up, right there. Yeah. Why is it 4?
So the first step for completing a square is cut this guy in half.
Okay.
Because when we were doing the examples like this, was that the middle term is always double this.
Okay.
So when we cut this guy in half, we actually figure out what this number is. Because that number is always, the middle one's always double whatever's in here. The last one is always the square of whatever's in there. So that's why the second step is square it. I think I left like 2 on there.
Yeah. Okay.
Yeah, so negative 2 squared is 40. Cool. Okay. Yeah.
How'd you get the other point, the 4-1?
By symmetry. So my axis of symmetry is there. It's 2 away. There's got to be a point 2 away on that
So
side.
there's just no calculations. It's just.
And you can double check it. So when you plug a 4 in, I get 4 minus 2 is 2 squared is 4 times 2 is 8 minus 7 is 1. So 4, 1 works. I did that very quickly, but you can all plug points in. Right? So whenever you get that other point by not calculating, you can check it by calculating. Plug it in. It's not a bad check. Okay. So the last little thing I want to talk about with section 3.1, and I am going to spare you this proof because hopefully the past teacher showed you this proof. I always show this proof in Math 103 and 110. So too bad for you guys, I'm not going to show you the proof. It might be in the book. I don't know, I can't remember. Yes, it is in the book on page 227. So it's the whole thing about, I'll show you the first step. Completing the square on this to find out what the vertex is. And this is actually where you get quadratic formula coming from. Right? So quadratic formula is this here. What is it? Somebody help me out.
B squared minus 4AC over 2A.
Yes, right? So you certainly should know that. Right? That should be no big deal. You should know that just as well as mx plus b. So tell me this. I want you guys with me here. And some of you guys already know this shortcut. There's a really nice shortcut for finding the vertex because this is kind of crummy. There must be some shortcut, and it has to be based on the quadratic formula because the quadratic formula is based on completing the frickin' square, right? So help me out here. If I had, where's his x-intercepts? Yeah, good. 1 and negative 5. Now, if you multiply them out, you'll get x squared, blah, 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 blah. So it's got to be a parabola. Can somebody tell me what the x value is for the vertex? Where must the vertex be compared to what I've drawn so far? Do it again. So compared to those intercepts, where must the vertex be? In the middle, because it's symmetry, right? One of them's got to be the reflection of the other dude, so the mirror's got to be right in the middle. So what x value is the vertex? Yeah, in this case, it's going to be 3 in, 3 in, negative 2. So the vertex must be somewhere on this line. Negative 2 comma something. You guys semi with me? Are my intercepts always that pretty? No. Now, sometimes they are this pretty, right? But the really cool thing about this equation is you can see, if I rewrote this a little bit, negative b over 2a, give or take all this crap here, right? Is that cool? I just can break it both up. They're both being divided by 2a. You with me? So my intercepts are this plus this and this minus this. What's right in the middle, it's almost too there to say. What am I adding and subtracting from? Give or take this from this guy. This guy must be right in the middle. Negative b over 2a must be right in the middle. You guys semi with me? So if I add and subtract from this to get my intercepts, What must be right in the middle? Well, it must be this. This must be right in the middle. That's what I added and subtracted from to get the x-intercept. So what's in the middle of the damn thing I just added and subtracted from? Negative b over 2a. Does that sound familiar to anybody? The shortcut for finding the vertex, negative b over 2a?
Yeah.
Some of you guys know. There you go. You have gotten a shortcut. Right? So, real quick, applying it here. So what the hell does this mean? I can find the x piece by doing this. How do I find the y piece? If I have the x, how do I find the y? Plug it in. So it's simple.
Negative 4.
So let's try it out here. What would the shortcut say over there?
Negative 8 divided by...
So we got this here.
Yeah.
I just erased my vertex. Don't you bet? The shortcut would say x is negative b over 2a. What's b?
8.
Good, negative 8, right? ax squared plus bx plus c. So the b is negative 8. And what's a? 2. So I get 2. Cool. Is that what we got for the vertex on that problem? Now that I've gone and erased it for myself?
Yes.
And then how do I get the y? I just plug it in. So if I plug a 2 in, what do I get here? I get 2 squared is 4 times 2 is 8, minus 16 is negative 8, plus 1 is negative 7. That sounds familiar. Right, it was 2 negative 7, the vertex. That kicks some serious ass. I mean, that's a very quick way to find the vertex. You with me?
Mm-hmm.
Sweet. All right. So does that mean I'm not going to ask you, of course not. Okay, I'm still going to ask you to complete the square in this kind of problem. Just so to make sure you can do it. Okay. So that's section 3.1. Let's do one example from there. These are nowhere near as difficult as what it sounds like, but let me go ahead and say what's part of this section. Pre-calculus word problems are in this section, right? And pre-calculus word problems basically are mostly maximization or minimization, optimization problems. I want to make the most money I can. I want to spend the least money. I want to make the most volume out of some material so I can hold the most stuff. You with me? That's optimization problems. And it kind of makes sense if we're talking about quadratic. They have maximums or minimums. If I can find it, what was the easiest way to find that? Well, we just did, right? So if I can get the equation, I can do negative b over 2a and find the vertex, and I got the answer to the problem. Not a big deal. Kicks ass. You make it sound nice, Jeff. Let's see. So if you got your book there, it's page 231.
What problem are we doing?
I think we're going to do, I'm just now picking one out. Let's do number 75. It's page 231, number 75. And they are excessively nice to you guys. Way too nice. So Carol has 2,400 feet of fencing to fence in a rectangular horse corral. So the perimeter is 2,400. Now they on the picture, do you see that they have stuff down there for the picture? Can somebody help me out? How the hell did they get there? Can you recapture what they got in the picture there? Now, if you don't have your book, which looks to be way too many of you, in the picture they have this. Where would those come from? So really, the best we can do right now would be that. I don't know what either one of those things are. All right, I got x by y. I don't know. But I do know that the perimeter has to be 2,400. So what's the equation for this perimeter? This is what they tell me.
X plus y.
They tell me the perimeter.
X plus y equals
2x plus 2x.
Yeah, you got to have Both lengths and both widths. Now you could do this. What I always do is just go halfway. If I go x plus y, then I cut that in half. Yeah. So you could start with, I think most of us know that 2w plus 2l, that thing. I have to have 2 lengths and 2 widths. If I cut everything in half, that's x plus y equals 1200. That's equivalent to going halfway. And then, of course, you just say y equals 1200 minus x. That's where the hell they got this. All right, so they did a little too much work for you. From everything I just said, you should interpret that as being, I'm not going to do that kind of work for you on the test. I'm going to expect you to do that. But this is almost every optimization problem. They tell you something. They got to give you some information. Here's how much material you have to work with, whatever. So that's the kind of problem here. Here's how much material you have to work with. They got to tell me something. I can set up an equation for it, and then I can say, okay, I want to use it somewhere. Now, what do they ask me about? What do they ask me to do?
Find the sides.
Find the function.
For what? Ah, cool. So they tell me about perimeter. They ask me about area. So, of course, now it's easy. What's the area function going to be? X times 1200 minus x, yeah. You just multiply length times width. Not a big deal. So you use what they tell you in what they ask you. That's why they have to tell me that. They have to give me something to work with, or else I'm like, I don't know. So that's part A, right? Find a function, blah, blah, blah. And then part B is the one that's got all the work in it. It says find the dimensions that would maximize the area. So what the hell do I do there? Well, what kind of function is this? No, I mean, what kind of function is this? Quadratic, I love it. That's a quadratic, right? Because when you multiply this through, what do you get?
Negative x.
Yeah, 1200x minus x squared. Is that cool? So, to find the maximum area, and why does it make sense to have a maximum? What kind of parabola is this? Is it open up or down?
Yeah.
Down, because it's a negative in front of the x squared, right? So it's very related to slope. So it's a down parabola. It's got a maximum. How do I find that maximum?
The graphic calculator.
No, bad answer. Right? I love it. And by the way, I'd love to do this. I'd love to have an entire class where we do everything completely by hand, and then the next class I'll show you how you can check yourself in the graphic calculator. Very rarely will I allow this to be your work, right? Unless they say on a test, use your graphic calculator to do this, and then that would be fine. So how do I find this guy's vertex? I love it. There, yeah, negative b over 2a. Now here's where you got to be really careful. What's b? 1200. Exactly. This is out of order, right? So it's ax squared plus bx. So b is 1200. I always get people throw that around. Just because you put it out of order doesn't make things change. So b is 1200. A is negative 1. 600.
So
And then, well, what does that mean?
So you plug 600 in for x in the function?
If they asked me for the area, and sometimes they would, I would plug it in here to see what the area is, right? But what do they ask me for? What do they actually ask me for? The dimensions, meaning the length and the width. So if x is 600, what's y going to be? 1200 minus 600.
how's that a rectangle?
This would say 800. Like that. It is a rectangle. It's a very specific kind of rectangle. The kind that has all the same side lengths, which is also known as a square. So it kind of makes sense to optimize a situation where I have 4 sides like that. Quadrilateral, it's going to be a square. A square will be the answer always. They will have problems where they say you're going to corral it and you have something that doesn't swim. So you're going to have one side is going to be this river that you hope doesn't recede far enough to go around, or that doesn't come up and drown them. That would be both two bad situations. Right? But you're going to have a problem like that. One side maybe better would be against the house. Right? So then you have, and now it is going to be a true rectangle. It's not going to be a square. But it also has its own pattern to it that you can see. You guys semi with me? So they just said, I got a rectangle, how do I optimize the area? It's going to be the square of that situation. So it's going to make a square out of your material, you're done. So you can pretty much bet that I'm not going to ask you that kind of question in the test. I'm going to ask you one where one side is against the house or something. Yeah?
I have a question. So when you do the ones with the ones that are up against the house, would you just subtract off that part?
So what you would do, now watch. If I had 2,400 feet of material again to use, right? And here, this would be X, Y, X. You with me? I don't count the house because the house is already there. Over. So what would my equation be for my perimeter? 2x plus 1y equals 2,400. So now when you solve for y, you would get 2,400 minus 2x. Not the same thing over there, right? That's what leads to a different answer at the end, is I don't have one side from the very beginning. You don't have to adjust for it later. You just use what you got. Okay, maybe. Okay. Most of these problems in here in section 3.1, they actually give you the equation already. And then you just have to do negative b over 2a. Those are, again, pretty much too easy. So enjoy those. All right. So the last thing I want to do today is get into section 3.2 a little bit. And then what we're going to do next time is we're going to sort of go over everything we went today, and I'm going to show you how to do some of the things we did on the calculator and do some other problems from homework. But I do want to get into 3.2 just a little bit. I have a little handout here. We'll see if I get to it. So section 3.1 is all about quadratic equations, which is a very specific subset of polynomials, right? They're just degree 2. They have the highest power of 2. Section 3.2 now says, I want to graph every possible polynomial. I want to know how to graph any polynomial. There's something that might be kind of new to some of us. So let me show you an example of the first little piece to worry about. Can somebody tell me, draw a very just rough sketch in the air of what that would look like? Can anybody? I like that. That's cool. That's tier 11. Now put it tier 11. Actually, what would that look like? It's an odd power. So it's definitely not going to look like what an even power would look like, which would be parabolic. It's going to look like that. Now, to 11th power, it's going to be really skinny. It's going to rise damn quick. 2 cubed is 8. So the cube goes up pretty. 2 to the 11th power, okay, right? So it goes up really damn quick. So my scale is really big on my y-axis here. You guys with me? But the shape is the same as any odd power shape would be. So we call this end behavior. Especially when I start throwing in there other pieces. So if I had something... Now I know that this definitely looks like that. I just don't know yet what those specific points will be. You with me? But I know the shape. And knowing the shape is so freaking important. You can fill the points in. Anybody can just calculate them. Who cares? You got to know the shape in the first place. So of course, real quick, if I had this instead, if I had g of x equals x to the 28th power, what would that look like? Yeah. Gold. Right? And if it was negative, it would just be pointing down. And again, it's to the 20th power, so that's damn skinny. It goes up way super fast. So any odd power is going to look cubish. I call this cubish. Another instructor here calls it the giraffe graph because it looks like... But I always thought that was evil because it's like a giraffe that lost its front legs. It's just going to fall over. It's really mean. And of course the other one's just parabolic. So no problem. I'll call it parabolic and I'll call this cubish. Right? What gets weird is when I start having smaller degree terms in there. That's when I start having this kind of weird shit happening, right? I have all these little inner bumps going on. So it's looking like Loch Ness Monster. So I have something like that.
Nice.
So real quick, why would there be some major difference? Well, because when x gets really small, when the values I'm plugging in for x are really tiny, this gets stupid tiny. Right? Tiny to the 11th power is stupid tiny. You guys with me? 0.1 times 0.1 is 0.01. So numbers that are smaller than 1 get even smaller when you multiply them. Right? So these then become very much more important the closer you get to 0. So around, on the outside, way on the outside, away from 0, it's got to look like this. All these other things can't match up. 2 to the 11th power just kills all these dudes. They're all dead. They don't matter at all when you're talking about 2 to the 11th power. If I had $1 billion and $1 dropped out of my pocket, I'm not going to jump for it as much as I would right now. Right? It's all relative. So, but the trick here is, I really want you to understand, this problem, it's got to look like this on the end. It's got to. Because that's going to take over for big x's. Big positive, big negative. What's going to happen in the middle, I don't know yet. It's going to be some kind of weird shit, right? But that's part of what we're going to talk about is how do you determine, in a kind of a rough way, not a perfect way, a rough way, what the shape is generally on the inside. But right now, this is called end behavior. And you can always tell the end behavior by the largest power. What degree the polynomial is. You guys with me? Anybody with me? One person, all right. So all this other stuff doesn't mean a damn thing when you're really, really big, but this guy doesn't mean much when you're really small. That's why in the middle I've got to leave it blank for right now. I don't know. So this, when I say what's your end behavior, don't draw a complete graph, just draw the outsides. So if I had a function like this, let me see. Let me throw a curveball at you. Now, the form of that is fundamentally different from the form of this. I will save some of you. The highest power is not 3. What would the highest power of that be if it was like this? Yeah. The highest power in here is 2 times 1. X, that'd be x cubed, times x cubed is x6. So the end behavior should be like x to the 6. So what should the end behavior be like here?
Field goal.
Yeah, field goal. So up, up. Leave the middle part blank. Right? The quickest way to answer when I ask you what's the end behavior is to draw it. Don't fill in the middle part. Sometimes I have somebody fill in the middle part exactly right. I'm like, you're doing the calculator already and letting me know you are. That's not a good idea. Right? To go one step further, what are the x-intercepts?
2, -5.
Yeah, when it's like that, it kicks ass. Somebody already factored this for me. So my x-intercepts would be 2, 0, -5, 0,
7, 0.
7, 0. I love it. Cool. I think we're going to try to actually graph this thing. Let's see what happens. Alright, so here's the next interesting thing. What does a parabola do at its root? I mean, so what does a parabola do when it's approaching the x-axis at its root? It turns, right? So any even power is going to do that. What's next to the odd power do at its root? Goes through. It doesn't turn. It looks like it's going to turn and then goes out. You guys with me so far? So here's the really cool thing. That root of 2 came from something that's squared. So I know what this function does at this root. It acts like a parabola at that root. It actually turns at that root. So what would it do at this root? Would it turn or go through?
Go through.
Goes through. It's a first power. It's a line. A line is definitely going to go through its root, right? And what's it going to do here?
Go through.
It's going to go through because it's a cube. It's an odd power, so it's going to go through. So let me prove that to you a little bit better. That's what's called using the multiplicity. What the Huda? This has got a multiplicity of 2. And really the multiplicity is just saying how many times does it show up. So if I said this equals 0, your answers would be this, but how many times does this show up as an answer? Twice. This shows up once. This shows up 3 times. So if somebody's multiplicity is even, it's going to turn at the root. If somebody's multiplicity is odd, it's going to go through. Okay. So let's look at that a little more formally. You can always do this also. And this is really good to do to get used to it, especially if you're going on to calculus. You're going to do a lot of what I'm about to do, just using calculus ideas. This function is 0 at 2, -5, and my scale is bad. I'll do it.
You're just looking at intervals of concavity.
So it's 0, 0, 0. Yeah, that's definitely way ahead of this. Right. We don't worry about concavity until Math 180.
Right.
Yeah. So I'm not going to say that word. So it's 0 there. Now the nice thing about polynomials, can they just suddenly say, I don't like here, I'm going to go here? Can they do that? No, they cannot do that. They have to be what's known as continuous. They have to flow. They can't suddenly pick up and go somewhere else. So polynomial could represent the flight of something, some plane, and you'd hope to God your plane didn't suddenly do that. Or, that. Right? First off, that would be bad, and secondly, that would be physically impossible. Okay? That's just some Bermuda Triangle believer. Sorry about that, but oh. So the only place that this could change sign, so if it's going along happy, the only way it could change sign is by going through the x-axis. Do you see what I mean by change sign? All the outputs up here are positive. The only way it could have negative outputs is to actually go through the x-axis. So I call this a door. Right? So all my x-intercepts are possible doors. You can't just suddenly appear on the other side, transport over there, right? Maybe. You guys are all like, just do it, dude, whatever they're going to do. All right. So the whole idea is, if the only place that it can possibly go through is at x-intercepts, if I look at one value and it's negative, that means it's negative between those intercepts. It's negative for that whole little region. It's got to be. It can't change sign unless it's a freaking door. So if I check, for example, if I plug a 0 in, what do I get when I plug a 0 in? Don't even tell me the number. Tell me the sign. I get positive times positive. I'm plugging a 0 in, right? Times negative. So overall I get negative. So it's got to be negative all the way through there. Then it could change sign here. And it could change sign back there because it's actually going to 0 there. Now what else might it do if it has a 0? It might turn. That's what I was talking about with the multiplicity. So that actually is a shortcut to what I'm doing right now. So keep going. Plug a 3 in, what do you get? This is always going to be positive times positive times negative, right? If you plug a 3 in, 3 minus 7, negative, so it's negative. You with me? I don't care what the number is. You guys with me? All I care about is what the sign is. So again, it's negative out here. How does that jive with what I said about 2 earlier? Let me make sure you're just with me. So how to get this here? I plugged a 0 in. You can plug whatever the hell point you want to in there. I'm always going to use 0 if I can. I plugged a 0 in, and it was negative at 0. If it's negative at 0, I know the scale's wrong, but if it's negative right here, it's got to be negative all throughout that area, right? It can only become positive if it goes through one of these zeros. That's why you only need to check one point in those little regions. It's awesome. Allow it to be awesome. Now, what did we just find out? Does it change sign? Does it go through? No, it actually touches at 2. Isn't that what we said was going to happen here? It was like a parabola at 2. So it should touch. And this actually showed me it does. It comes up from the negative and it touches 2 and then it keeps going negative. It turns there, right? You with me? Some of you guys? So keep going. What happens out here when you plug an 8 in? Positive, positive, positive. So it's positive up here. Sweet. And that makes sense because it's supposed to, it's an odd multiplicity. It should go through. It should change sign. And it did. And what about down here? Plug a negative 6 in. Positive, right? Because it's squared. Times negative times negative.
So that's a positive.
That's a positive. And again, it changed sign through negative 5 like it was supposed to. Because it's an odd multiplicity, right? It's like a straight line through 5. So you have 2 different ways there you can look at it. And that's what, I'll give you that in a minute. We're almost there.
So then how do you graph it?
So excited. Oh, right here, you can do a very rough sketch of it right here. Yes,
So is that just finding intervals of increasing and decreasing?
not, well, sort of. There'd be an extra step to do. I have to do the turning points, and we didn't look at the turning points. These are just roots. So yeah, that's still math 180. So look what this says. What do I know about the end behavior of this? It's up and up, right? And look, it's positive there and positive out there. That makes sense. It's up forever. On the ends, it's got to go up forever. It better be freaking positive out there. You with me? Does that make sense? What's it going to do now? It's going to go down to 0 at 5, right? Let me draw like a little imaginary axis here. So at 5, it's going to go through 0, and it's going to go through to the negative. And then what's it going to do at 2? It's going to touch and stay negative. And what's it going to do at 7? Go through and go positive. So now it's got the right end behavior. It's got to go up on both sides. It's going to do weird shit in the middle. Because it's got all these, if you multiply this out, it'd have a bunch of little x to the third power, x squared, x, all those little smaller degree terms. It's going to make you go all bumpy in the middle. Okay, I'm using very technical talk, right? Bumpy in the middle. That works. That's what it is. So that's not good enough for a final answer, but that at least tells you what it should end up looking like. Right? So if I want to actually graph this thing, here's where it's going to get a little ugly, because I wasn't careful with my numbers. Somebody help me out. Let's figure out what my scale should be here. What is the y-intercept? Oh, it's big. Negative 6,860. So how did I try to get that? That might be right. How do you find the y-intercept?
So there's x equal to 0.
So x equal to 0. So then you get 4 times 5 is 20 times negative 7 cubed, which I think is 343. Twice that is 686 times 10 is 6,860. It's negative. Somebody check me out there. I don't know if I trust my brain here. So I have to be able to get all the freaking way down. So I can kind of double check my little rough sketch. At 0, I should be at negative, whatever I just said. 6,860, right? Is that right? Oh, that's what nobody's checking out. So we'll just go, we'll pretend like that's right. Okay, thanks.
Sorry.
That's right. So one big part of this will be you have to pick an appropriate scale. You obviously are not going to always want 1, 2, 3, 4, or else you're going to be on the floor taping pieces of paper together just to get to your freaking y-intercept. Right? That's crazy. So you want to pick a good scale. So I want to be able to go down to like 8,000, so maybe 2,000, 4,000, 6,000, 8,000. There's 7,000, 8,000. So my
What did you say 0 was at?
negative 6,860.
Yeah. Correct.
Thank you. So it's roughly right there. I can basically put it right on 7,000 because it doesn't have to be perfect. I'm more worried about the shape of this than I am about exact positions of things. This scale can still certainly be 1, 2, 3, 4, 5, 6, 7, 8. And of course, the scale's got to be the same, 2,000, 4,000. So my x-intercepts, let me do some work. My y-intercept is right there. My x-intercepts were 2, 0, negative 5, 0, and 7, 0. So here, I kind of know what it's doing here. And does it match up with my rough sketch? Yes, thank God, right? You guys see, I kind of know this is parabolic. I really don't have to plug any points in to get any help. And what's it doing after this point? Going up forever, right? So I know what it's doing here. Now, I don't want to go too far here. I want to see how far up here is it going. Because what's it going to do, not up here, but what's it do at 2? Turns around. So I want to know how far down it goes. So it's got to come into 2 and turn around. So how do I figure out how far down it goes, roughly? It's not going to be perfect.
972, negative 972.
Did you graph it and you're looking at it? All right, so be quiet.